Hello, calculus fans. Let's find the area of the region bounded by the graphs of y equals 8 over x squared, y equals 8x, and y equals x. Let's look at the picture, and we need to come up with any points of intersection. All right, so this is a rough sketch. I don't want to interpret this as being to scale. It's sort of a reasonable picture. I know that y equals x and y equals 8x are lines. It's probably not a great picture because I don't think y equals 8x is, I don't think I have it steep enough, but let's not worry about that. It's very often that we'll draw pictures that are not to scale. Okay, let's find the x-coordinate of the intersection point between y equals 8x and y equals 8 over x squared. It'd be good if you had a graph of this thing hanging around so that you can follow along with this. Okay, usual thing, we'll set them equal to each other and solve for x. Multiply both sides by x squared, and so that gives us that x is equal to 1. All right, now let's find the x-coordinate of the intersection point between y equals x, that's the lower line, and y equals 8 over x squared. Same deal, set them equal to each other. 8 over x squared is equal to x. That gives us x cubed is equal to 8, so x is equal to 2. So now let's divide up this region, and I've got a new picture that I want to look at. All right, so now it looks like this. I've got two different regions, call them A1 and A2. Notice that you can see the x-coordinates of those intersection points, that was 1 and 2. And I've divided them up into two different regions because for each region, the top bounding curve is different. Let's look and see what the top bounding curve is like for this region. This is the top bounding curve. That's the line y equals 8x. For A2, the top bounding curve is y equals 8 over x squared. So the top bounding curve switches depending on where you are in this region. And that breaking point happens at x equals 1. So this is the dividing line between those two regions. All right, so we're going to compute each area separately, and that's because each region has a different top bounding curve. You do the same thing if they had different bottom bounding curves. All right, so let's compute A1. A1 is the integral from 0 to 1 of 8x minus x. The top bounding curve is y equals 8x. The bottom bounding curve is y equals x. Go back to the picture to have a look at that. All right, so we get the integral from 0 to 1 of 7x dx. All right, get your younger brother or sister to evaluate this integral for you. This is the easiest integral you're ever going to run into. 7x squared over 2 evaluated from 0 to 1, so we'll get 7x. Okay, now A2, a little bit more complicated. That's the integral from 1 to 2. So those are the bounds inside the second region. You're going from 1 to 2. Those are the x bounds. Now the top bounding curve is y equals 8 over x squared. The bottom bounding curve is the same, so that's why we're subtracting x. So you see both regions had the same bottom bounding curve, and they had different upper bounding curves. Okay, this is also not so bad to integrate. Minus 8 over x, minus x squared over 2. Plug in 1 and 2. We subtract, we get something that looks like this. And that works out to 5 halves. So if you want the total area, you just have to add these two up. Area is A1 plus A2. And it comes out to 7 halves plus 5 halves, and that's 6. All right, so we had to break up this region because the top bounding curve changed. You'd have to break it up if the bottom bounding curve changed too. There's nothing really special about the top curve. Okay, that's all for now.